I got into programming basically because of a mistake. I had to decide what to do when I got my student exam, my high school exam, and I decided history was a great thing to study, but it was a lousy career and it could be a good hobby, so I picked mathematics. But studying mathematics, I wanted to do something practical, something that had some appeal beyond pure math. And so I signed up with what in Denmark was called mathematics with datalogi. Datalogi is a Danish word for computer science. I didn't know that. I thought it was a branch of applied math. So I was signed up for this, and then I discovered two things. One, that I wasn't as good at math as I thought I was, which happens to most math students. And that programming was really fun, machine architecture was really fun, and well, took it from there. And when I was mostly through my master's in mathematics with computer science, I decided that I liked machine architectures, and they had some really nice machines in England and some people working with microprogramming and things like that, really low-level stuff. So low level that the slogan was assembly code is for, not for real programmers. So I decided to get a PhD at Cambridge, went there, it worked out, got my PhD, needed a job. I wanted to get a job back in Denmark because it's a really nice place, but they didn't have any jobs for people with this kind of speciality. So I'd been over-specialized, over-educated for Denmark. But then Bell Labs suggested I drop by and talk to them. And well, it's the best place in the world for applied computer science. And when they gave me an offer, of course, I said yes. And so I ended up in the States doing sort of applied computer science, which in my case turned out to be, I started with distributed systems and tools for distributed systems, and then that became C++. But it all started with sort of an ignorant student picking something he didn't know what it was. One of the things I like about computing and programming in particular, it's the best excuse for looking at any field, because they all use computers and they all use some programming. So a thing that keeps me going is I visit places where they use C++ and see what they are doing. And so I get to CERN and to JPL and also lots of little places. I was with somebody who was programming coffee machines. So you can see a lot of things, a lot of interesting things by being in computing. That's a very hard question because the industry has become so broad and so varied. And I think a fundamental mistake that people are making these days is to think that computer science or computing or IT or whatever is one thing. And so in universities and some training courses, they try to teach people who are going to engineer life-critical systems. They teach them in the same way as people who are making web apps in JavaScript. And these are very different topics, very different tool change, very different mental outlook of the people that's doing it, very different skills. And I think the industry is so broad that we have to stop thinking about it as one thing. And the education, the training should take that into account. Where the future is going, I don't know. It's going all over the place. As I mentioned, there's coffee machines with C++ code in it. The AI, ML, everybody is studying this these days. I mean, almost all of the low level of that is C++ too. Is it the same kind of people? Actually, remarkably, some of the techniques are the same in anything that's close to hardware and has performance requirements. But really, large-scale AI and coffee machine programming is not quite the same. And yeah, where's it going? I think we're probably seeing an overproduction of AI specialists. This has happened before with just about anything that becomes popular. All the students go in the same direction. All the startup goes in the same direction. Even the startups that hasn't got much to do with it throw it in so that they have the buzzwords. And well, something else will come along. But when I started in computing, I don't know how many computer scientists there was in the world. I don't think 10,000. How many millions do we have now who could call themselves computer scientists? And then in addition to that are all the people that write scripts and maintain and put up web apps with tools and such. I don't know, tens of millions. There's just so many. I think because I had a fairly clear view of what I and my friends needed, and because that happened to have something to do with performance and flexibility, I set off on a good path. This was part luck, part good education, I guess. But basically I decided I needed a language that could do high-level things and low-level things. Low-level things because, well, we all use hardware sooner or later, and somebody has to deal with it even though it's messy and changing. And we want to get away from the hardware, so we have to have abstraction mechanisms. And I think doing that, I then made the decision I wasn't going to build just a solution to my own problem. I was going to build a tool for things that needed, for projects that needed this combination. And that has been a very successful thing because there's been a lot of such things. Just about any embedded system has aspects of that. And most high-level, high-performance constraint system, anything from a 40,000, 60,000 processor server farm to a wristwatch fits that description. You have to deal with the hardware, you have to abstract from it so that you can be productive and reliable. And then C++ grew up at Bell Labs, which at the time was the best place for practical computing in the world. There was an amazing range of problems and amazing range of skills and people and a supporting environment. And so instead of trying to build the final product, I realized that I was building a tool and that the tool had to grow. All good engineering depends on feedback. And so I built something, I see how it works, I do experiments, and then I grow the language a little bit to match the needs of people who are actually using it or want to use it. And so it's an evolutionary strategy, more or less from the beginning. Had a lot to do with the fact that it was just me and I didn't have that much support and no marketing and such. So the only way of succeeding was to serve the users better. And so grow it like that. Then we got a standards committee which makes growth more difficult, but stability is a major part. And one of the reasons C++ lasts is that it's stable over decades. And a lot of people build systems that need that kind of stability. So you have the combination of stability and evolution. We don't change dramatically in breaking ways. It may look as if we're changing dramatically, but the old code still works. One of the key ideas is that you want to reuse some code that exists as opposed to build it and then reuse it. And so that means that you have to encapsulate things that are old style or you may not like or may not be as safe as you would like it, but you encapsulate it, put the old stuff into the new stuff, and then that allows you to have both stability and evolution. Very interesting idea really, especially in retrospect. And you can see C++ going from one researcher to maybe 5 million developers or more, and not disappearing. Every year there's a couple of hundred languages being designed, implemented, and a couple of hundred dies. Yeah, and then of course it takes some luck. But the education and the environment Bell Labs was very important. I think the fundamental design decision for C++ was sound, and I think I could do all the details better. The key to a language succeeding is actually that it meets a need. And Dennis Ritchie said there's languages designed to solve a problem and a language is designed to prove a point. The latter ones tend to die, and certainly C and C++ is in the to solve a problem. But it also means that they are not as pure and clean as some people would like. Sometimes they have features for experts to do expert-like things, and that they confuse novices and university teachers, for instance, who has never actually had to face that kind of problems. So yeah, lots of languages are designed, a couple of hundred a year, maybe more. It's easier to make a language these days. But getting people to use it is another matter. Does it really address the problem? Does it really address the problem better than the existing languages? And how will the existing languages respond? Will they learn and adapt the new techniques? Will they have a library that can do things just as well as some of the newer languages? And so it takes time for a language to mature to the point where it is useful for people who didn't actually implement it in the first place. You have to have some principles when you start, a fundamentally good idea. And you have to have it fairly general, because you don't actually know what the future is like. It has to be something that can survive, and it has to be able to change. And then you have to work heavily on the community. I wasn't very good at that. C++ is totally chaotic in terms of its community. There's not a single user group and such things. I should work more about that. But one thing I learned, and I think I got right with C++, is that a language is only a language. It's only a very small part of the developer's tool chain. A language is surrounded by things like operating systems, IDEs, builders, package managers, analyzing software, and around that again is user groups and conferences and teaching stuff. It's sort of a very broad thing, so there's a huge human component in it. In the center you have the language, which is what people talk about, but I had for my talk today a list of about 20 or 25 things that wasn't the language but was necessary for a developer to do the job properly. And so I would work much harder about that. I would also try and set up an organization that would be in charge of the language or whatever it was. I never managed that because I never had money enough to set up anything permanently. And you can't have everybody contributing directly. You need somebody that makes design decisions, make decisions about direction, but you can't have just sort of one person trying to do it on his or her own, because, well, nobody knows enough to do that. So that's sort of for the future. For the past, you need a time machine. I actually give a time machine question to some of my students. Basically, take your time machine, your TARDIS, go back to the early 70s and tell Dennis what he could have done better. And then flip up to the early 80s and tell me what I should have done better. But remember that they know the time and the context at the time better than you do. And most of the things we do today couldn't have been done then. Dennis Ritchie, who did C, started with a machine with 48K of memory. I started C++ with 256K of memory. Wow, I got a good stuff. And I actually thought that soon I'll get a megabyte. And so C++ and C grew up in that kind of very constrained environment. And those people sort of can't imagine running a program without a couple of gigabytes. Well, these languages were designed to handle small things, and there's lots of small things, a lot of small embedded systems. I talked to a guy the other day who was building 4-bit microcontrollers for power, for surge protection, surge protectors. And he was writing in a fairly modern C++ style. Now, it is technically not possible to have 8-bit C++, but if you cheat a little bit, you can do it. C++ can touch the hardware, so you can get it to work even though it's not part of the standard. And there you're back to the kind of world with a couple of kilobytes of memory. In my time, there just wasn't that many jobs in Denmark in IT, and they were specialized in things that people did in Denmark. And now I was doing something that wasn't done in Denmark, and a lot of people thought if it wasn't done in Denmark, it wasn't worth doing. A little bit of sort of not invented here. Not everybody, but enough to make the job market very scarce. And if you wanted a university level job in computing, you usually had to wait for years for a position to come available. The US was very different in that respect. There were several possible places. If you want a university job, there's all kinds of universities. Getting into an Ivy might be difficult to teach, but then there's a second and third tiers. There's always a job. Similarly, with the job market, it's just much bigger. Much bigger, meaning hundreds or maybe thousands times programmers at the time, many numbers of programmers. Today, with the net and with network conferencing, such, you can live in other places. It's good to have sort of friends and colleagues you can talk to, and there's things that, in my opinion, are not done that well remotely. So there's still an ideal of being close to others that do similar things. And with the uncertain job market, you have startups, 9 out of 10 fails. What do you do when your startup fails? You better be in a place where there's another startup you can get a job at. So people end up in such places. But today, I don't think I would have gone to the US if I was young. There's many more opportunities in Europe than there was in the time. And I would look for a nice place physically, a nice place to have a family, a nice place to have friends, and where there was some community of developers. And then you can take it from there. If it works, that's great, because you're now in a nice place and such. If it doesn't work, you can try something else. But that's true for any first choice or second choice or so on. I've been at very nice places visiting or lived there. I lived in Cambridge for some years for my study, and I was back as a fellow later. Great place, had those things, those properties. The French tried to set up a place at Sophia Antipolis in Antibes, which was absolutely great. But then the government changes their meaning of what's important. First it was computing, then it was biology, and I think it's AI. They changed the subject, and suddenly your technical area falls away because it was too dominated by a single entity, in this case INRIA, which had done superb work over the years, but also had this problem of changing. New Jersey in the US, where I lived for many years, were great, but there was only 2 reasons to live in New Jersey, in my opinion, which was Bell Labs and Princeton. And Bell Labs is not what it used to be anymore, and I'm not a full-time academic. So. But the balance between life and family and environment and the technical stuff. It's a balancing act. Yeah, it's hard to give advice, at least as hard as to take advice. Don't over-specialize. Don't be too sure that you know the future. Be flexible, and remember that careers and jobs is a long-term thing. There's too many young people think they can optimize for something, and then they find they've spent a couple of years or more specializing in something that may not have been the right thing. In the process, they burn out because they haven't spent enough time building up friendships and having a life outside computing. I meet a lot of sort of, I don't know what we can call them, junior geeks that just think that the only thing that matters is their subspecialty of computing, programming or AI or graphics or something like that. And well, it isn't. And the rug might be pulled under them for that. And if they do nothing else, well, if you don't communicate your ideas, you could just as well do Sudoku. You have to communicate, and a lot of sort of caricature nerds forget that. They think that if they can just write the best code, they'll change the world. But you have to be able to listen, you have to be able to communicate with your would-be users and learn from them, and you have to be able to communicate your ideas to them. So you can't just do code, you have to do something about culture and how to express ideas. And I mean, I never regretted the time I spent on history and on math. Math sharpens your mind, history gives you some idea of your limitations and what's going on in the world. And so don't be too sure. Take time to have a balanced life, and be ready for the opportunity. I mean, a broad-based education, a broad-based skill set, which is what you build up when you educate. You're basically building a portfolio of skills. Means that you can take advantage of an opportunity when it comes along. You can recognize it sometimes. We have lots of opportunities, but a lot of them we either can't take advantage of or we don't notice. It was my fairly broad education. I'd done standard computer science, I'd done compilers, I'd done multiple languages. I think I knew 24 at the time. And I have done machine architecture, I've done operating systems, and that skill set turned out to be useful.